Inside every large electrical transformer, hidden magnetic forces generate heat that must be carefully managed to prevent equipment failure. Consider a standard magnetic circuit operating safely at a baseline of 500 volts and a frequency of 50 Hz. At these levels, the system produces a specific, steady amount of heat, known as core loss. This total core loss is made of two distinct parts. First, we have hysteresis loss, which is the energy absorbed by the core material as the magnetic field constantly flips direction. Second, we have 150 watts of eddy current loss, generated by small, swirling electrical currents induced within the core itself. But then, the operating conditions change drastically. The applied voltage is suddenly doubled to 1,000 volts, and the frequency spikes to 100 Hz. Our objective is to determine the exact new total core loss under these extreme conditions, to gauge the true stress level of the system. We cannot simply double the original losses and assume that is the answer. To predict the exact thermal output, we have to decode the precise physics governing this specific circuit. This document outlines the raw data. We isolate the parameters of the initial safe state as case 1 and the stressed state as case 2. The text also provides a Steinmetz index of 1.6, a material-specific constant used to calculate hysteresis loss. Setting this up side by side organizes our approach. On the left, case 1 holds our baseline numbers. On the right, case 2 holds our spiked voltage and frequency, along with our material index. Organizing the data is only the first step. To calculate the new losses, we must establish the exact mathematical relationships connecting the voltage, the frequency, and the maximum magnetic flux density. Looking at the lower half of the document, we see the foundational equation governing the circuit's behavior. The RMS voltage, E, equals 4.44 times the frequency, times the number of turns, times the maximum flux density, times the cross-sectional area. Because the physical build of the transformer doesn't change, the number of turns and the cross-sectional area remain constant. Therefore, the maximum flux density, Bm, becomes strictly proportional to the voltage divided by the frequency. Now we look at the standard theoretical formula for hysteresis loss, denoted as pH. It relies on a constant, the frequency, and the maximum flux density raised to the power of the Steinmetz index. By substituting our voltage over frequency relationship in place of the flux density variable, we derive a new working proportionality. Hysteresis loss is proportional to the frequency to the power of 1 minus n multiplied by the voltage to the power of n. Next, we examine the standard equation for eddy current loss, PE. It is based on a constant, the frequency squared, and the maximum flux density squared. We execute the exact same substitution here, replacing flux density with voltage divided by frequency. Notice what happens when we square that fraction. The frequency squared in the numerator and denominator cancel each other out entirely. This leaves a simplified proportionality. Eddy current loss is solely proportional to the voltage squared. By deriving these relationships step by step, we uncover an important physical reality. Frequency spikes have zero impact on the eddy current losses in this specific system. Moving to the calculations, we set up a ratio between case 1 and case 2 for hysteresis loss. Plugging in the raw data, pay close attention to the frequency exponent. 1 minus the Steinmetz index of 1.6 results in a negative 0.6. Solving the ratio gives us our first concrete answer. The new hysteresis loss, pH2, increases to 800 watts. We shift focus to the eddy current calculation below, setting up a similar ratio based on our voltage-only rule. Because frequency canceled out, we only insert the voltage data, 500 over 1000 squared, simplifying the math. Calculating that fraction reveals that our new eddy current loss, PE2, surges to 600 watts. We have successfully isolated the variables and quantified the exact damage caused by the voltage and frequency jumps on both mechanisms of core loss. To determine the ultimate stress placed on the transformer, we combine these two newly calculated losses. As highlighted at the bottom of the page, we add the 800-watt hysteresis loss to the 600-watt eddy current loss. This gives us our final value. The system is now generating a total of 1400 watts of core loss. That represents a massive increase in thermal energy trapped inside the metal core, pushing the system hard toward its physical limits. By tracing the equations back to their origins, we avoided the pitfalls of simple memorization. Knowing exactly how these variables interact is the most reliable way to accurately predict a system's failure point when operational conditions suddenly change.